Okay, so let's continue. So we're talking about CRCs, and CRCs is a way to calculate the check bits using binary arithmetic, binary division of binary polynomials with each other. So if we have the generated polynomial and the information polynomial, we first start by adding zeros at the end of the information polynomial, and then we divide through with the generator to figure out the remainder, and the remainder ends up here. So then at the end of the day, we have a code word, which is the information bits shifted to the left plus the remainders, the check bits, and therefore we get the information bits here and the check bits here. So this is a systematic code because we have the data here plus the parity bits here. Okay, and now to check whether a received word is a code word or not, we can repeat the process, and for all code words, the remainder will become 0. Okay. So just as we did with the internet checksum, we calculated the checksum and then added the parity bits at the end of the checksum of the data. And then if we redid the calculations on the checksum for that is the original data plus the check bits, we get a checksum which is 0. So the same process applies here. So it's easily seen actually that we know that the code polynomial C is x to the n minus k times I of x. These are the information bits plus the remainder. Okay, and then what is the remainder here? Well, we get that by taking these information bits, shifted to the left, and then divide through, by g, and then calculating the remainder. So we can write this xn to the minus k times I of x as some quotient q times g plus the remainder. Okay, so that's just by definition what the remainder is. Now, so let's see what the code word, how we can write that. Can we factorize that in g? Yes, we can. So c of x is x to the n minus k plus ix plus rx. Okay. And then we plug in what x to the power n minus k times ix is, namely qx gx plus rx. Okay, so this is that part, the first part, and then we add on the remainder at the end. And now, what is the remainder plus the remainder? 2 times the remainder if this was usual arithmetic, right? But it's binary 2 addition, right? So when we take 2 binary polynomial and add them together, we add the coefficients modulo 2.
Just zeros.
Exactly. So this is equal to the 0 polynomial. Okay. So what can we say then about the remainder of c when we divide with g? Well, it's the old 0 polynomial. Okay. So if we want to check a pattern, a polynomial, whether this is a code word or not, we simply divide by g and then check whether the remainder is 0 or not. If the remainder is 0, the pattern, the polynomial, is a code word. If the remainder is not 0, then the pattern or polynomial is not a code word. Okay. So the encoding, that is to find the parity bits, and to check whether a pattern is a code word or not, is the same process. We just do this, and if we at the end get all zeros here, we know that what we started with was a code word. Okay. So what we do then is to plug it in here, right, in the beginning, and then just do this. Clear? Okay. So then what CRCs are there? Well, there are many. Here are just a few of them, maybe the most important one. If you go to Wikipedia, we see a much larger table, and I'm not sure if that is even exhaustive. So essentially one wants to find these generator polynomials. And to find the generator polynomial is actually quite involved process, both mathematically and then also maybe experimentally. So we won't go through the details here. We'll just, somebody else did this work for us. And there are a number of CRCs that are so special that they have their own names. There's a CRC32, the CRC16, CCITT, and CRC1, for instance. These are three common ones. And then the 32 here means that there are 32 check bits. Okay, and then we need a polynomial here, and the polynomial should have degree 32 plus 1. Okay. So here we have 32 bits, and then there is a 1 at the end. And for 16, we have this polynomial, so it's 16 bits plus 1. And for the CRC1, it's just 1 bit, and then we have very simple polynomial 1, 1 here. So this one is actually something that we know already. This is a single parity check code. Okay. So one can see that to generate the single parity check bit, we can use a CRC if we like. Okay. So this is not, okay, so that's just saying that the single parity bit is a special case of a CRC. Now, this CRC32 is used in quite many different types of standards. I'm not sure if we can, if you recognize all of these, but Ethernet is one of them. Okay. So Ethernet, at the end, there is some trailer in the Ethernet frame, and these are 32 check bits from a CRC32. Okay. This CRC16 is used in many other things, Bluetooth, for instance, here, a bunch of other things. And then this single parity bit is used in, it's all over small hardwares, right? So it's a simple error detection thing. One thing one should be a little bit concerned about is that when one looks into table and want to figure out the polynomials here, there are many ways to represent a polynomial. So you can have the bits in this order or that order, or you can represent them in hex digits and octal digits and so forth. So there, if you go to the Wikipedia, you see the different forms that are available here. One should remember that since there is always one leading one in this, typically these are not even mentioned. So then one just mention the rest of the bits here, which is a nightmare when you want to implement this, because then you will get the wrong thing without actually knowing it sometimes. So one has to be careful when, if you want to implement a CRC, you go and you check what is the polynomial. That's what you need to do. Make sure that you understand how the polynomial is specified in the table, because otherwise bad things will happen, right? And it's not maybe immediate that bad things happen, because you use a generator polynomial which will generate a remainder, but the resulting code might be very bad. And if you don't, and you might not notice that until you start to use it. And then it's maybe a little bit too late. Right. Okay, questions? No, okay. All right, so where are we now in the course? We have, last week we talked about the physical layer, which is responsible for shuffling bits from point A to point B. We know that some errors will occur on this channel. So what we have done now, we have talked about error detection codes in order to detect whether errors have occurred or not. And we could do that using a good CRC. These codes are quite good, actually. So they're fairly good. They're not perfect, because there are no perfect things in the world, but they're quite good. Okay. So what we will assume now from now on is that we have some mechanism for checking whether a receipt packet is in error or not. And if the packet is in error, we need to do something about that. Okay, so that's our next step now. So now we're going to go back to protocol layers and talk about layers and how different layers can provide services to the layers above them. And one thing that typically or often we would like to have is a service that guarantees that the received information is correct, or at least gives a very high confidence that the received information is correct, even though we know at the physical layer errors will occur. Okay. So now we will talk about protocols to ensure that this happens. Okay, so going back to protocols, and this is a very quick recap of what we did early in the course. We have layers, services, and protocols, and we know that the protocol lives in a layer. Okay, so in layer n+1 there are two software processes, two entities, or two peer processes is the same thing, that communicate with each other, exchanging protocol data units, and then executing a protocol according to the rules of the protocol. Okay, so that's what a protocol is. This information is virtual in the sense, so it's only logical. The physical connection is done using the services of the layer below it. And so this entity here, when communicating with that entity, is actually, instead of sending its PDU of this logically the PDUs goes like this. Physically the PDUs goes down in the stack until it hits physical layer and then being transmitted over. Okay, so this PDU is then shifted down here into this layer. So in the layer below it, and here this is then changing name from PDU to service data unit. And this service data unit, the protocol at layer N puts on a header to that, and that forms the protocol data unit for that layer. And that's then sent back and forth logically. Physically goes down to the stack. When it hits the physical layer, that actually is when the transmission occurs. Okay, so we remember this, hopefully. So we have peer processes. These processes that work on the same layers called peer processes, okay, because they're on the same hierarchical level, right? They communicate with each other using a protocol, and the protocol data units is carrying the data back and forth in order to execute that protocol. Right, and the service data unit is what you get from above. You add your headers, typical protocol headers like this. So this is called encapsulation, and you don't look into the data here. You don't use that in order to execute the protocol on this layer, because this information is useful for this protocol. It should not be used per se with this protocol. And then there is a service access points here. Right, we remember this, hopefully. Okay, so the idea of a protocol is to provide services for the layer above it using the services below it. So each layer should, hopefully refine the service, the quality of the service, until we are at user level where we have a very nice network communication service. Okay, service models then. So how should we characterize services? And here, this is quite fuzzy, I would say. I mean, there are many ways to do this, but one can say there are some properties that is associated with the service. So a service has some features, and some features are quite natural and some maybe less natural. But for instance, if I'm at the layer and deliver a service up to the layer above it, I can say, okay, my service can handle these and these things and has these and these properties. Okay, so that defines the service which I'm providing up. Okay, and one thing one can tell the layer above it is that, okay, I can transmit data messages of a certain size. Okay, either I can say, okay, I can only transmit bytes, 1 byte at a time. That's my service. Or I can say, I can transmit 1500 bytes in a chunk. So if you give me data in chunks of 1500 bytes, I'll be happy to transmit those. Or I could tell the layer above it, just send me something and I will take care of it. So you can send me unlimited size, gigabytes or gigabytes and gigabytes of data if you like, right? So the different levels of service here when it comes to message size. I can also tell the layer above it that the the service data units you give to me, I will deliver them in order at the other side. Or I can say, I'm not going to guarantee that they are delivered in order, so you have to fix that yourself if you like. So sequencing, whether we deliver in order or not, is one property. Reliability is the third one here, to say that, okay, whatever data you give to me, I guarantee you I will deliver that. Or I say, give me the data, I'll do my best, no guarantees. Okay, different types of services. Multiplexing is basically to say that, okay, I can serve several of the protocols above me, or processes above me, or I could just serve one. Okay, so this is called multiplexing. Timing, pacing, and flow control. We haven't talked so much about this, but timing could be say that, okay, you give me a packet, I promise you to deliver that within 2 milliseconds. Okay, so that's a promise on latency. Or I can say that if you give me packets every 200 milliseconds, I will deliver them every 200 milliseconds also in the regular pace, right? Flow control essentially means that if I have a receiver which is limited in its buffering or processing speed or so forth, I promise you I won't overload it with packets. So I will transmit packets in the regular speed that receiver can handle. Okay. And then a service could also have some confidentiality. That means that the data will be treated confidentiality, so encrypted and so forth. There could be something with integrity, which means that whatever I deliver, I guarantee you that every single bit is correct. Authentication basically means that we're signing the packets that we are transmitting. We'll talk more about this later on. Okay. So there are many ways one can define a service, and of course, the better service we have, the more expensive it is, right? That's why we have different levels of service in protocols as well as in regular life, I guess. Whatever service you buy, you're willing to, you want the quality for your money, right? But if you don't have so much money, then you have to live with the lower quality. It's just a fact of life, I guess. Okay, there are two main ways to provide communications. One is connection-oriented, the other one is non-connectionless. Connection-oriented simply means that we establish a connection between the endpoints before we start to transmit data. So you can think about the telephone system here if you like, or you can think about TCP if you know how TCP works. I'm not going to go through this so much now. Connectionless essentially is that there is no whatever data I get, I treat them as a one-shot transmission. So I get a service data unit from above, I just transmit that. And then I get another service data unit, I just transmit that. And I don't try to keep track of these in any way. I don't establish a connection with the receiver. I don't know if the receiver is alive even. Right? I just send it and hope for the best. And examples of this is UDP and IP, which is quite useful, right? Even though it's less quality maybe than a connection-oriented service. Message sizes, if there are, typically there's at lower layers, there's always a bound on how much data they can handle, the lower layers. So if you want to hide that for the upper layers, you need to somehow, if I get a gigabyte above and I know that the layer below me can only transmit 1500 bytes at a time, of course, I have to take this gigabyte and chop it up and then send it individually. This is called segmentation. It could be also that the layer below me has to have a minimum number of bits to work, and then sometimes I have to take two SDUs above and paste them together to send to the lower layers. So this bookkeeping of chopping up and gluing together SDUs is something a protocol can provide. Reliability, we will talk more about this later on. So, and here we use error detection codes and retransmission protocols. So that's what we're going to move into in 5 minutes, I hope. Flow control is essentially that we are not overwhelming the receiver, which means that we cannot just if the receiver is limited in its capability, we cannot just blast it with a lot of data, because then there will be buffer overflows at the receiver, and it might even crash. Right? So we have to be a little bit careful about this also. TCP does this, for instance. And timing is for some real-time services, for instance, real-time video or video call, for instance, or Skype conversations and so forth. The delay is quite important here. So then one has to control that also. We'll see a few examples of that later on. Multiplexing, we talked about that, servicing several entities above. And privacy and integrity, we will talk about that later on. Okay. So this was a quite quick review of what we did earlier in the course, and now we're going to move into new things here. So suppose we want to provide a service here, for instance, reliability. We have end nodes where the data originates and where the data should be delivered. And here, these are the end nodes. And in between, there are many different intermediate nodes, routers, switches, and so forth. So if one wants to ensure reliability, then for each hop we are transmitting, there is a chance that there will be an error. Right? So how are we going to protect for errors? Are we going to protect on the individual hops, or are we going to protect from end to end? And the answer to this is that we need essentially to do both. Okay. So error control, should we do that at every hop or only between the source and destination? So if we have here two end nodes that needs to communicate with each other through several routers here, for instance. Here's the information flow goes down, then over a physical layer, up in the network layer, down, up, down, like this. Okay, so each layer here could potentially provide some type of error control, right? It is trying to do its best. So the physical layer, for instance, we designed the modulation format to be as robust as possible for the channel that we are using, right? So we're using good pulse amplitude modulation with nicely chosen pulses, right power levels, and so forth. Nevertheless, even though we are doing our best on this layer here, there will be some remaining errors from here to here. So in this virtual link, right? There will be some errors here. Then the data link layer here could try to clean that up by using retransmission protocols, for instance, or something like that. And then provide a service on this layer, which is better than the service we had here. Okay? We're trying to improve the service as we go up here. So here there might be also some error control. And transport layer might do the same, and session layer also maybe. So where should we put all this error control? That's not really clear. But one thing one can say that is that errors can occur anywhere and will occur anywhere. So at the end of the day, on the top layer here, we probably need some type of error control. Right? Because it's not even enough if we had a perfect physical layer here, no errors here, what could then possibly go wrong? Well, this is a physical piece of hardware. It can break. It can be a power outage. Something could go wrong internally in this machine. So even if this is perfect, maybe data is lost here, right, due to a power outage or a hardware failure. Right? So we cannot guarantee performance on the top layer here by guaranteeing performance only at the lowest layer. We have to do it layer by layer. Okay. And consequently, we need something on the top layer also to handle errors. So this is typically what is done. We have layers and layers and layers of error protection. What is the pros and cons with this, right? Because hop-to-hop error control cannot guarantee end-to-end correctness. We talked about that because of hardware failure in the intermediate nodes, for instance, or something else. Hop-by-hop error control is good, especially when the hops are unreliable. For instance, suppose we have a super good physical layer here, then there are very few errors remaining here on the data link layer, and it might not even be cost effective to try to clean them up at this layer. Okay. But if the errors are here, significant errors left here because the physical layer is not so high performance, then we need error control here. So this hop by hop error control is good, especially when the hops are unreliable, but less important for reliable hops. Because if they're reliable already from the start, there is not so much to clean up. Hop by hop error control, that really increases network complexity, which is something that we don't want to do, right? So we don't want to have error control there just for the sake of it, because it's going to cost us. So therefore, at the end of the day, a combination of end-to-end error control and hop by hop, especially for those hops which are unreliable, that tends to be a good design. Okay, so how are we going to do this? So now there was a lot of yada here, right? But let's now assume that we have something, a link, a hop, which is unreliable. And that hop could be a hop over one physical link or over several links if we're on a higher layer in the protocol stack. But anyways, we have two entities, two protocol entities that are talking to each other over a server which is unreliable. How can this protocol correct or make the service more reliable for the layer above it? Okay, so to make it clear, we're living in a layer. We're using a service below us, which is unreliable. We want to provide reliability up. How are we going to do that? Okay. The principle is that when we send data, we protect that with the error detecting code. So at the receiver, when I get the data from the layer below me, I check for errors. If I detect an error, I ask for a retransmission by communicating with my peer on the other side of the network. Okay. If the protocol, the data I get is correct, I send it up. If it's wrong, I throw it away and ask for a new transmission. That's the general idea. How do I know if the data is correct or not? I use an error detecting code, a CRC, something like that. If the CRC checks, I assume everything is well and I send it up. Is that process perfect? No. So sometimes I send up something which is wrong. Rarely, but it happens, right? If it doesn't check, I know for sure something goes wrong on the channel, and then I ask for a retransmission. So very simple main idea, right? But we will see the devil is in the details here. This is actually more complicated than it sounds. So the first, okay. So what we would like to do now is provide a pretty good service that delivers packets in order, without errors, and without duplications. Okay. And we see that we will see soon that if we don't do our protocol design correctly here, bad things will happen in terms of this, right? We will reshuffle data, we will deliver things with errors and sometimes with duplications. So the basic elements here, we need an error detecting code, a good one. We need some timeouts, as we will see, some clocks, and we need some special packets which are called acknowledgements that says that data has been delivered correctly. And sometimes we also need something called negative acknowledgements or NACs. So we need ACKs and NACs, at least ACKs. Okay, so a first attempt of this retransmission protocol, just basically executing what I said earlier, is that at the transmitter side, what do? We get data from above, service data units from above. So then we create a frame or a packet, PDU, same thing. What do? I take the service data unit from above, add some check bits to it, and then a header, right? But I add these error detecting check bits, header and error detecting bits, and then I transmit that frame using the layer below me. So data, check bits, headers, and so forth, and push it down. And then I start a timer. Okay, so when I transmit the data, I start a timer. And the idea here is that if I don't hear anything from the receiver within a certain time, I assume that the data got lost, and then I retransmit on my own initiative, right? So, however, if I get an acknowledgement from the other side saying that things went well, then I can accept the next packet from above, and then redo this process. Receiver, what do we do? The receiver will get data from the layer below it. It would check the frame for the parity bits, check whether these parity bits are okay, so CRC or internet checksum or so. If the data is good, or I think it's good, we deliver it up, and at the same time, I transmit an acknowledgement packet back to the receiver, back to the transmitter. Okay, so check for errors. If no errors are detected, deliver up in the protocol layer, and send an ACK. If errors are detected, what do? I don't know what to do, right? Because if I receive a packet that's in error, how can I trust it? I cannot trust the header, right? It might not even be for me. I cannot trust the destination address. I don't know the source address. I cannot trust that. So the safest thing to do is just to throw it away. Okay, and I can do that because I know that at the transmitter there is a timer. So eventually, if the transmitter doesn't hear from me, it will send the packet again. Okay, so that's the safest thing to do. Okay, so let's see a timing diagram for this. So we have the transmitter and receiver, and here we have two time axes. And now things will happen in a sequence here, and we see how the protocol is executed. And now let's assume that things are good. So normal operation. Normal operation is that frames can be lost. Okay, that's part of normal operation. However, acknowledgements, the remaining frames, for the time being, we think they are never lost. Okay, and timeouts are longer than the turnaround time, and we'll see what that means in a second. Okay. So here we go. What happens? I'm standing here at the transmitter. I get some data from the layer above. Okay, good. So what do? I send it. Okay, and what do I send? I send the service data unit I got, which has a number 0. Okay, so this is a time index. And then we put the header on that, and then a CRC. Okay, so this I assemble that and put that down to the layer below it, which transmits that. At some point here, it reaches its destination. Okay, so what are the destination? Okay, and at the same time, when we transmit, we start a timeout also. Okay, so what happens here is that the receiver checks this and say, okay, that's a good frame, right? CRC bits are okay, then delivers that to the layer above it. Okay, and transmit an acknowledgement back. In the acknowledgement, it has some data in it saying that it belongs to this packet and so forth, right? There is some data in here, and that data needs to be checked for errors also. So typically one use error detection also in the reverse way here. Okay, and then this one arrives before the timeout hits here. Okay, so this is what I said with normal operation, that the timeout we do here is longer than the turnaround time. The turnaround time is from here to here. Okay, so that then things are good. Then we get the next packet, and we transmit that. But it's okay to lose frames. We said that is part of normal operation. So what's going to happen now? Well, the receiver has no clue, right? It has no idea that something has happened. So it will for sure not send an ACK. And then when the timer expires, the transmitter say, okay, something bad happened, and then retransmit the same frame. Okay, this frame is then delivered. Okay, is this clear? All right. So what could possibly go wrong? Let's see what happens when these two things are no longer okay. So that we can lose acknowledgements and that we have a timeout here that sometimes is not correctly set. Okay. So why can ACKs be lost? Of course they can be lost because they're transmitted over the network. Why could this happen? Well, it's because this turnaround time here depends on the time it takes for the packet to go from end to end or whatever between the two protocol units that are communicating here. And that delay could be variable in time, right? Because it depends on the network load and many things, right? So it might not be super easy to set this timeout. So sometimes we might be, and we don't want to set this to several hours, right? We want it to be as short as possible so we can recover as quickly as possible. So sometimes we're a little bit greedy and then bad things happen. Okay. So what happens here then if we have problem now, number one, when we lose ACKs here. So suppose everything went well here, and then we transmit an ACK, but it's lost. So what is the transmitter going to do? Resend, exactly. So it resends here. What's the receiver going to do? It's going to accept it, right? You see the problem? What's the problem here? Duplicates. This is not good, right? So suppose these are two parts of a video or something like that. We're going to, you know, the playback is going to be all screwed up. Or two parts of an email. It's going to be duplicated. It's not good. We don't want that, right? So we delivered two identical STUs in this case. And so lost ACKs could lead to duplicate the STU delivery. Not good. Okay. Problem number two, timeouts, premature, which means that we transmit a data. Now we're taking away headers and CRCs and so forth. It's assumed to be there, right? So the data comes down here, is delivered, but the timeout hits before the ACK of that STU reaches the receiver here. So here the receiver gets nervous and retransmits the STUs at this point in time, while the ACK here just reaches the transmitter here. Okay, so we're going to deliver here again duplicates. Right? What else could go wrong? Well, if this packet is lost, the ACK from the previous STU might reach the transmitter within the timeout interval here. And what is the transmitter going to think here? It's going to say, oh, good, I got an ACK for this packet, while the ACK is actually for that packet. And then it will send number two and so forth, right? So what do we see here? The delivered packets will be duplicates sometimes, and sometimes not at all. Bad, right? Okay, so what are we going to do about this? Any suggestions? Oh yeah, increase the timeout, that's right. And also make sure that the ACKs are never lost, right? Okay. Okay, another, do we have another suggestion? So this is things we have to live with, of course. Okay. Well, actually the key is already here. We see here that when we deliver this, we see that there is a sequence number here, right? Okay. So what we want to do then is at the receiver, or at the transmitter, attach sequence numbers to the data we transmit. And at the receiver, we need to check that the sequence number of the STU we receive is actually correct, what we expect it to be. And therefore, we can avoid this, right? And in the same thing, the ACKs that we are sending back also has to have a sequence number attached to it. So, for instance, when this ACK is transmitted back, the receiver will understand that it has to do with the data unit number 0, not, sorry, when this ACK comes up here, it's due to sequence number 0, not to sequence number 1. Right? So then the transmitter can resynchronize itself. Okay, so we need sequence numbers. So the main idea is then that we enumerate the transmitted frames, 0, 1, 2, 3, etc. And at the receiver, we inspect the packets and see, okay, we expect 0, 1, 2, 3, etc. And if we get them out of order, we do something about it. Okay, so we transmit frames with sequence numbers, and then we make sure that that sequence number is also part of the acknowledgement. So we are using sequence numbers in both directions. These are known as some type of state variables, and state variables are sequence numbers, could also be other things, but it's somehow keeping track of the state of the communication, right? So in TCP, for instance, there are several other state variables, but here's an example of a state variable. The transmitter can keep track of say, for instance, the sequence number of the oldest sent frame, which has not yet been acknowledged. Okay. So, for instance, when I get SDUs and I send them, I keep track of the oldest frame that has not yet been acknowledged. Okay. And when I get an acknowledgement for that frame, then I move my state variable to the oldest one that I still don't know whether it has been arriving or not. The receiver state variable is a sequence number of what it expects. Okay. So when we start, for instance, the first frame I transmit is 0, and then my state variable is 0, and then I transmit 1, and then my state variable is still 0 because I haven't heard anything from the receiver yet. And the receiver expects that the first frame it gets is 0. Okay. And then when it gets 0, it says, okay, and then my next frame I would like is 1. When I get 0, I then send an ACK over here, and then the transmitter knows, okay, so 0 was okay, so then I can forget about that, but I'm still unsure about frame number 1. Has it arrived or not? So we try to keep track then at the transmitter and receiver of what we have sent, the oldest packet we have sent. That's what I keep track of at the transmitter. At the receiver, I keep track of what is the next packet that I expect. I need to keep track of these two numbers. And if I do, then I know what to do when I get something which is out of order. Okay. So in the simplest case, we use something called stop and wait. And what happens here is that I get a packet and I transmit that, and I do nothing until I have that acknowledged. Okay. So then the transmitter needs to maintain a state variable, which is actually just binary. We could have 0, 1, 2, 3, 4, etc. We see that this is a problem if I am sending 2 gazillion packets, right? Because at the end of the day, I need a sequence number which is 2 gigabytes long, right? So that's not going to be good. I need to reuse my sequence numbers. Okay, the fewest bits I need for a sequence number is 1. Okay, so let's try if that works. Okay, so the transmitter has a state variable, which is slast, and it's either 0, 1, and the interpretation of this is the sequence number of the last transmitted frame. So the first frame I send is frame number 0. Okay, so it has sequence number 0. So I send it, right. If I send frame if I get an acknowledgement of this, then I can send the next one. The receiver maintains a state variable, which is the sequence number of the next expected frame. So it will be 0 if the last corrected received frame had number 1. Okay, because then it expects 0. It will be 1 if the last correct received frame has sequence number 0. Okay. So it will toggle between these two things, just as the transmitter will toggle between 0 and 1 depending on which frame it's sent. Okay. The acknowledgement we send back will have then will inform the transmitter of the receiver state variable, so R next. And for reasons which will become a little bit obvious, we actually invert that bit. So the ACK frame here will be R next and then the CRC. Okay, I'm sorry. The frame that we are actually transmitting is the sequence number, the frame, and then CRC bits. the ACK frame will be rnext and the CRC. So the receiver and transmitter are communicating their state variables with each other. The receiver will accept the frame if it has sequence number S last, if and only if S last is what it expects to receive. That is when S last is equal to rnext. Okay, I think we're going to break here and then pick up this thread on Monday. And what we will see then is that by introducing these state variables, we will be able to correct for lost ACKs and premature timeouts. And we can actually provide in-sequence delivery of correct frames. Okay, so see you on Monday.